Hello and welcome to Unit 6, which will be in two parts. So this is 6A, and we're going to be doing some work with circles. So these videos will be covering some sections that we'll do about circles. And the first section is segments in circles. And today we will have you identify, sketch, and define segments related to a circle, determine whether or not a line is tangent to a circle, and find the lengths of segments in circles. So we're going to start by doing some defining and sketching of lines and segments related to a circle. So we're going to start with radius. And a radius is the segment from the center to any point on the circle, such as this segment right here. We'll call this OA. That would be a radius. Center is O. So of circle O, segment OA, like this with the segment symbol above it, would be considered a radius. Now a chord would be also a segment, and this time the segment has endpoints on the circle. So a chord can go through the center of the circle, but usually we name a chord like this. We kind of have the endpoints on the circle. It goes from one end to the other. We'll call this AB, and we say segment AB is a chord. Now, when the chord does go through the center of the circle, then we actually have a special name for it. We call it a diameter. So that's what we'll see next. A diameter is a segment that passes through the center of the circle. So note, a diameter is what we call the longest chord of the circle. So maybe like this, right there. So we'll call this segment CD. Okay, so that's segment CD. Okay, now a couple of lines. We're going to talk about a tangent line first. A tangent line is a line that intersects the circle at exactly one point. So I always say that a tangent line is a line that sort of taps or touches the circle and then just continues on. So taps or touches the circle. That's what we call a tangent line. So I'm going to call this T, and I'll put another point on here so we could name it. And so this could be called segment TV. And a secant is different than a tangent in that it actually intersects the circle in exactly 2 points. Okay, so I always think of this more like a sword for a secant. Like it goes in and comes back out. It has to intersect the circle in exactly 2 points. So let's say we call this M and this N, then this could be line MN. So note that all the segments and lines that we've named are all named with 2 letters. And even if we were to go back and maybe name the center of the circle, like here, call that circle O, we still wouldn't call this segment COD. Okay, so we only use 2 letters to name a segment or a line. All right, on the next page, we're going to name an example of each of the following in the diagram that's given. So here we have circle Y. And for circle Y, we have lots of segments drawn in and even some lines in the picture. So it's going to be up to us to name all of these things. So we're going to name at least one of each. So a radius could be YX or maybe even YT. So we'll just put down YX. Then a chord, in this case, I won't name the diameter because I'm sure I'll have to name that separately. So we'll just do RW. WR would have been okay as well, but just not WZR or RZW. Tangent is that segment or line that taps or touches the circle. So there are 3 letters on that segment, so I'm just going to use 2 of them. So I'll just say QZ. That's a tangent. Diameter would be maybe TX. We could call it TX or XT. That would be our diameter. And finally, our secant didn't come all the way out, but it does actually intersect the circle in 2 points. So we'll call that VT. There is our secant. Now, the point at which a tangent line okay, intersects the circle to which it is tangent is called the point of tangency. So we're going to refer to this point of tangency in the next couple of theorems. Okay? So we have what we call a point of tangency. So like in the above picture, Q would have been considered a point of tangency right there. Okay, so we're going to get the tangent radius theorem next. And the tangent radius theorem says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Okay. So you've got this tangent segment. Okay, so we'll just kind of point out these parts. You got this tangent segment here. If a line is tangent to a circle, then it forms a right angle. It's perpendicular to the radius. Okay, anywhere you were to draw a tangent, let's just say we drew one right here. We'll say we're tangent right here. If you were to draw a radius to that point, it would be another perpendicular. As you see, like you can just tell it makes a right angle. So anywhere you draw a tangent line and connect it to a radius, you're going to get a right angle. So that's what we call the tangent radius theorem. Now, it also works backwards, okay? And we call that the converse of the tangent radius theorem. And it says, in a plane, if a line is perpendicular to a radius, meaning if we can show that there's a right angle, okay, at the endpoints of the circle, then the line is tangent to the circle. And that's what really we're going to be trying to use. We're going to be trying to show that a line is tangent to a circle. So we're going to want to show it's perpendicular. So the easiest way to get a right angle is to use Pythagorean's theorem. And that's what we're going to see ourselves using. So we can use these theorems along with the converse of Pythagorean's theorem, which we just covered. So you'll remember this. So the converse of Pythagorean's theorem to decide whether or not a line is tangent to a circle. So if I want to know, let's say looking at this picture down here, if I want to know if AB is tangent to the circle, I need to know if there's a right angle right here at B. And I could tell there's a right angle here at B if these three numbers satisfy Pythagorean's theorem. If C squared equals A squared plus B squared, then I will have a right triangle and a right angle. So that's what I'm going to want to check. So to decide whether or not AB is tangent to C, I'm going to want to check to see, is C squared equal to A squared plus B squared? So now our C in this problem is 61. That might be kind of hard to tell. So, if you're not sure what that 61 represents, you may need to draw it out. In certain problems, that 61 is going to represent the whole side. In other parts, it might just represent this. So we'll let you know, what that given number is actually going to be representing in the problem. But for this problem, that 61 is the entire side, which is the longest side, so it would have to be C. So I want to know, is 61 squared equal to 11 squared plus 58 squared? Okay. So if I do 61 squared on my calculator, I'm going to get 3,721. But now try 11 squared plus 58 squared. If you do that on your calculator, you actually get only 3,485. So actually they're not equal. Okay. In fact, C squared is actually greater than A squared plus B squared. And do you remember what that means about the triangle? It actually means it's an obtuse triangle, okay? But we wanted to know if it was a right triangle, and that was a no. So we would have to say ABC is not a right triangle. Okay, triangle ABC is not a right triangle. So AB is not tangent to circle C. It kind of looks like it is when you look at the picture, but based on the given information about the sides of the triangle, we now know it's not. So let's try another one, and let's see if we get a tangent this time. Okay. So this time they gave us some information to plug into the picture. So it says segment CB is equal to 9, and AD is 82, so that's all of that. AB is 80. Okay, and so really I would want to also fill in that CD is 9, so I have all of that side. Okay, so I want to know, is c squared equal to a squared plus b squared? So let's check it out. Is 82 squared equal to 18 squared, because of the 9 plus 9, added to 80 squared? 82 squared is 6,724. And check to see, how does that compare to 18 squared plus 80 squared? Okay. Oop, and it's the same. That means this is in fact a right angle, which means AB is in fact a tangent. It's forming a right angle with a radius. Okay. So triangle ABD is a right triangle. So segment AB is tangent to circle C. So we saw one case when it was no and one case when it was yes. And then we showed all the work that proves our answer. So I'm going to give you a chance now to pause the video, and I want you to try a problem. Okay, so let's do the you try problem number 4. Okay. Okay, so hopefully you got a chance to check, to try this one on your own, but I did want to let you know about that 24. So this is that kind of weird situation where 24 couldn't possibly be the biggest side of the triangle. The other two sides are bigger. They're 36 and 48. So what this means is we had to be kind of clever. Since this is a radius, it's 36. This would also be 36, and we're going to have to fill that part in. So that could be a little bit tricky on this problem, which really means that this whole side, this possible hypotenuse, if it's a right triangle, would actually be 60 units long. And so we want to check to see, is 60 squared equal to 36 squared plus 48 squared? Okay, so let's check that out. 60 squared is 3,600. And then you want to type in your 3,600 plus 40, or I'm sorry, your 36 squared plus 48 squared, and you also get 3,600. So since this triangle satisfies Pythagorean's theorem, that means angle D is a right angle, and that means that ED is tangent to the circle. So angle D is a right angle, and that means that segment ED is tangent to circle F. So if you have any other questions about the radius to a tangent line or point of tangency theorem, then just let your teachers know when you're in class. Our second theorem today is even a little bit easier. This is called the two-tangent theorem. And the two-tangent theorem says this. It says if two tangent segments are drawn to a circle from an exterior point, so something outside of the circle, like you see point C over there, then those segments are, let's see what we can figure out what they are. Okay, so BC and DC, how are they related to each other? So I'm going to draw in a couple of segments to try to help us out. Now, since I know that B and D are points of tangency, as soon as I draw in a radius here, I get a right angle. That's the radius to a tangent theorem we just learned. Okay, if I do the same thing over here, another right angle. And now I'm going to connect the center of the circle to C, and I've made two triangles. And these two triangles each have a right angle. They're formed by radii, which of course are always equal to each other, and then a shared segment, which happens to be a hypotenuse. So these two triangles are actually congruent based on, if you remember the theorem HL, which is the hypotenuse leg theorem. Since the triangles are since the triangles are congruent, then all of their parts are congruent, which means BC is congruent to CD. That's the two-tangent theorem. If two tangent segments are drawn to a circle from the exterior point, then those two tangent segments are congruent. Okay, so anytime you see a picture with two segments drawn like that, tangent to the circle, and we have that given information, we have these points of tangency, drawn from that same exterior point, you can see point C is outside the circle, you can set them equal to each other. And that's what we'll do on the next couple of problems. So in problem number 5, it says AB and BC our tangent. So right away, that has to equal that. Find BC. Well, since they're equal to each other, I just have to set up a quick equation. 7x plus 9 equals 9x minus 3 in order to solve for x. So let's go ahead and subtract 7x on both sides. So 9 equals 2x minus 3. You can add 3 to both sides. And we will get 12 equals 2x, which means x equals 6. So now they want us to find BC. So I know that BC equals 9x minus 3. I'll substitute in 6. 9 times 6 minus 3. 54 minus 3. 51. And that would be our answer. And that is our BC. Now in problem 6, we're going to see a couple of theorems used in this problem. It says, encircle Q below, D and U are points of tangency. As soon as I see that, points of tangency, I'm going to go right in and put my right angles. Because those are radii that are connecting to those points of tangency. Now it says the diameter of the circle is 16 and QA is 17. All right, QA is 17. That's that segment right there. The diameter is 16 and there's no diameter drawn, but there are 2 radii. And a radius is half of a diameter. So this will be 8 and this will be 8. Find the perimeter. Okay, well, we know that this segment is equal to this segment. So we want to find those segments in order to get the perimeter of the whole figure QUAD. Okay, we already know these two are 8 and 8. So since we have the right triangles, we can use a quick Pythagorean's theorem. 17 squared equals 8 squared plus b squared, or 289 equals 64 plus b squared, minus 64, 225 equals b squared, which means b is the square root of 225 or 15. So now we have 2 sides that are each 15 and 2 sides that are each 8. So when we're going to get the perimeter of QUAD, we're going to add 8 plus 8 plus 15 plus 15. Perimeter is 46. So we're able to use the 2-tangent theorem and the radius to the tangent line theorem to help us find the perimeter. I think there's one problem for you to try on your own. So you can pause the video now and try this problem. Well, segments BA and BC are tangents. Okay, and 2 tangent segments are always equal to each other, so we can set up 4x plus 2 equal to 2x plus 8. Solve for x is all we want to do in this problem, so start by subtracting 2x on both sides. 2x plus 2 equals 8. Minus 2 on both sides. 2x equals 6. And x equals 3. And if I wanted to check my work, I could plug the 3 in, make sure that they are both equal to each other. 3 times 4 is 12. 12 plus 2 is 14. 3 times 2 is 6. 6 plus 8 is also 14, so they are equal. So that is the end of section 1. If you have any further questions, please ask your teacher in class. Have a great day, everyone.